Hi everyone. Happy to be here. My name is Justus. I'm an assistant professor in software engineering at the Vrije, so very close here in Zout. And I will be taking a bit more of a software architecture perspective on the topic of green AI. So I will talk to you about the challenge of designing green AI-based systems. First, a few words about myself. I'm in the software and sustainability group at the Vrije. So we are a classical software engineering group, but with a twist that each of us has a focus on sustainability in some way. So most of us are focused on environmental sustainability, so energy efficiency of different kinds of software systems. But we also have people who are focused on social sustainability, so who, for example, research bias or negative impacts on society of software. I started at the Vrije last year in August. Before that, I was a postdoc at the University of Stuttgart in Germany, where I led a division that was called Software Engineering for AI and Microservice-Based Systems. The latter part of this is because my PhD was on the vulnerability assurance of microservices, but you can imagine that's probably not why I'm here today. So I also do other research, mostly from a software architecture perspective. And I'm very interested in internal software quality attributes, so maintainability, evolvability, but also since I joined the S2 group at the Vrije, environmental sustainability. Most of my research is applied nowadays to AI-based systems, and that's because that's why I'm here today, basically, to talk about this. I also have an industry background, so before going full-time into academia, I worked as a software engineer in industry for more than 9 years, even though it was mostly in part-time. I was first at Hewlett-Packard, and then when this company split up again and again, I finally ended up at DXC Technology. So even though I never consciously changed my employer, I already saw 3 large enterprises from the inside. There I did a lot of software development, so I wrote an ungodly amount of JavaScript and TypeScript because I was developing front-ends. I had software architecture responsibility and gave a lot of customer presentation and workshops. And why am I telling you this? Because all of this heavily influenced my perspective on how I do research. So because of this, I highly value practical applicability of research results. I do a lot of state of practice studies, so to find out what people in industry are doing, but also which challenges they are having, so that we make sure that we tackle the right challenges. And then I also highly value collaborations with companies, like case studies, for example. So what will I talk about today? So I will first start with a short introduction to software engineering for AI, which is the field I'm currently most active in, and we'll talk to you about what that is and why it's important. Then I will take more of a software architecture perspective on this. And lastly, I come to the most important part. I will then talk about green AI from a software architecture perspective. So let's jump right into the first part. So what is this software engineering for AI and why do we even need it? So probably you are no stranger to challenges that companies might be facing when they want to adopt AI and machine learning. So typically you need specialized expertise here that revolve around machine learning models. Even if you don't train them yourself, you still need a lot of expertise. Sometimes this is called AI literacy. If you train them yourself, you will need a lot of data. And you may also require large computing resources for this training, sometimes even specialized hardware. But let's say, imagine for a moment we had all of this. So even if that would be the case, then there are still a lot of statistics that you can find, depending on which source you refer to, that a large percentage of machine learning projects never make it into production. So they are never turned into a production system. So this source is from 2019, so hopefully the percentage has gone down a bit by now, but in that source they claimed 87%. Depending on which source you look at, it's somewhere between 60 and 85, but it's still massive compared to general software and IT projects. So the question is, why is that so difficult? And one of the reasons for this, I think, is that historically we kind of had a divide between AI on the one hand and then software engineering on the one hand. So maybe if we briefly survey the people in this room. So who here thinks you would count yourself more towards the AI side of things? Raise your hand if you do. So 1 person, 2 persons, maybe 4. Okay. Who here counts themselves more towards SE, so software engineering? So that's definitely more. Some people didn't raise their hands at all, so they didn't want to be classified into this thing here. So, okay. Definitely, there are also very few people who excel in both of these domains. So some people even claim they are so rare that they are called unicorns. So it's really difficult to have deep expertise in both AI and software engineering. And that's also understandable because they focus on kind of different things. So in AI and machine learning, we focus a lot on data and algorithms, so the concrete machine learning models. And then we focus on their accuracy, so via metrics like precision and recall, and then small incremental improvements to these metrics. The process that we use is also more exploratory in nature, so it's much more data science than a structured software engineering approach. And typically we will work in notebooks like Jupyter or Armored notebooks. On the other hand, in software engineering, we at least like to have clear requirement specification. We don't always succeed at this, but this is at least something we try to strive for. And if we could have very simple, clear requirement specification, we probably wouldn't even need to use AI, because if we could simply implement it in if X do Y, we wouldn't need AI. We also focus on many different software qualities, so not only prediction accuracy, but a lot of different qualities that we often trade off against each other. So quality assurance and testing is also very important in this domain. We also prefer more structured processes, even though through agile and things like extreme programming, we also have a lot of iterative or even chaos-infused processes these days. But still, we like to have a bit more structure in these processes. It's not as exploratory as in data science typically. And then, of course, we like to think about software architecture and design. So to really focus on coarse-grained structures in our systems and products. And for a successful AI system, both of these actually are necessary. So both of these sides need to come together and talk to each other to create effective systems. So some of the challenges that you find in these systems are, for example, that you have a multitude of different roles that you need here. So you may have data scientists, data engineers, maybe software engineers that implement the non-ML components. You may have MLOps engineers and so on. So a lot of different people are involved with different expertise. The development process is also fairly different. So it's often very data-centric and focused on the model development, and then you need to bring it together with the more traditional software engineering process. You also have probabilistic results of the system, and these are difficult for a number of reasons. So first, it's very difficult to specify requirements for this, but it's also difficult to test and verify. And lastly, it's also difficult to communicate to your customers. So what do you mean the system will make errors? I'm paying you that it won't make errors, so you are telling me this is unavoidable. This is of course also a very different paradigm for some stakeholders. And by nature, these systems are often very highly interconnected, heterogeneous and distributed. So they are not the only systems of this nature, but they are an especially challenging case. You will also have new quality concerns that maybe are not so important in other systems. Things like explainability, fairness, also the energy efficiency. They play a much larger role in AI-based systems than in different other systems. And as you might imagine, all of these challenges, they have an influence on many of the phases that you have in a software engineering process. So on the requirements, but especially on the architecture, and then on the quality assurance and operations. So to tackle this, a new discipline kind of tries to emerge. And this one is called software engineering for AI, or also AI engineering. And what we are trying to do there is that we want to take a system-centric and software engineering informed perspective and approach to creating AI-based products and systems. So I also very much like the definition that the Software Engineering Institute in Pittsburgh has for this. So for them, AI engineering is a field of research and practice that combines principles of different disciplines. So systems engineering, software engineering, computer science, and also human-centered design. And with the goal to create AI systems in accordance with human needs for mission outcomes. So I very much like that they highlight that this is kind of an interdisciplinary approach here. So it's not only about AI people, it's not only about software engineering people. We need a lot of different expertise for this. But yeah, as you might imagine, and that's what I'm trying to tell you here, that software architecture of these systems plays a very important role. And this is the second part that I briefly want to talk about before I get into green AI. So just to bring everybody on the same page what I mean when I talk about software architecture. So you will of course find many definitions of this, but I briefly want to show you two ways how it's described in literature. So one is from this seminal Software Architecture in Practice book by Len Bass and colleagues, and it's a very structure-oriented definition. So it's kind of from the old world where they define software architecture as the set of structure that you need to reason about a system. So these structures are basically software elements, so very generic, then relations among them, and then properties of both of those. So this is kind of the old view of software architecture. The new view takes a bit of a different perspective. It's a rational-oriented one. And here we think of software architecture as the set of architectural design decisions. So now you just need to understand or define what architectural decisions are, and this is not very easy. But typically this is about decisions that have a large consequence for the majority of your system, especially those decisions that are hard to change later on. Oftentimes these decisions will involve trade-offs. So you might gain something for one quality attribute, but you might lose then something for another one. Oftentimes this could be something like maintainability versus performance efficiency. So other trade-offs might be security versus usability. So the perfectly secure system is one that nobody can use. But yeah, in the context of AI, you have often this trade-off, maybe you've heard about it, prediction accuracy versus energy consumption. So the higher your prediction accuracy, the higher in this case also will be your energy consumption. And I will come back to this a bit later. So when I made this slides, I thought if I really should include it, because I think there might be a lot of people in the room that have architect in their title, and typically you don't need to convince these people that what they're doing is important. But I still thought maybe have it for completeness sake. Maybe I don't need to convince you, but let me briefly tell you why I think software architecture is important. So firstly, it will allow you to reason about very large systems by using abstractions in hierarchies. So it kind of supports managing complexity. It cannot really reduce it substantially, but it can at least make it easier to manage this complexity. Secondly, it is the driver for software quality. So not what the system does, but how it does it. So if you have a system or a program that only needs to run once, that will never be executed again, it's not important how fast it is. It can run on a single machine. Only a single person will develop this. Then the software architecture doesn't matter, because if you don't have any quality requirements, you can put everything in a single file, in a single function. It's not important. So software architecture will play an important role if you have high demands for software quality. It will also enable you to decompose your system into several parts so that different teams can work on it in parallel. And lastly, it is kind of the bridge between the requirements and the implementation. So if you have a very complex system, then it will be very difficult to directly go from the requirements that you have to the implementation and start working on this and start producing code. If you don't first think about the large-scale structures in your system and how you allocate functionality to components, then this will be very difficult to implement. As you might imagine, reusing existing architectural knowledge is something that is very attractive and beneficial, because you can use it to increase quality and reduce effort. And there are different concepts in software architecture that are useful for this. So you may have heard of architectural styles, for example, of patterns, tactics, or reference architectures. And one of the reasons why it is still so difficult to create high-quality AI-based systems is simply that this reusable architectural knowledge has just started to build up. So we don't have a lot of architecture knowledge in this space yet that we could reuse to gain certain quality attributes with these systems. So what you're looking at here is a picture from a paper from 2015 from Google. And this was one of the early papers that talked about machine learning systems and technical debt in them, but also their architecture. And this little black box here in the middle is supposed to represent the actual machine learning code. What they wanted to show with this is that machine learning enabled systems have a lot of components, these other boxes basically, that are not exactly running machine learning code. So they are kind of non-ML components. So even though some of them might be very specific to AI-based systems, because they might be for the data management or for the model training or monitoring, they still are fundamentally normal quote-unquote software components. So the actual ML code can sometimes be a tiny part of this. I also very much like this approach by Geoff Halton. He has a very nice book, Building Intelligent Systems, where he talks about the high-level elements of intelligent systems. So typically you will have an AI engineering team that specifies some kind of system objective, and then the system will try to optimize for this objective. And of course, as you might imagine, that's already the first step where things can go wrong, if you set the wrong objectives to optimize for. But then the other elements are also not trivial. So he differentiates between the intelligence creation. So this is the part that actually produces the intelligence, quote unquote, for example, the machine learning models. And then there will be an intelligence implementation, which will run the intelligence and execute it. And then there is the intelligent experience, which will take the prediction results to actually present it to the users. And this is also where the experts for human-computer interaction come back in, if you remember this interdisciplinary approach I was talking about. Because this is also where a lot can go wrong. So when end users interact with an intelligent system, you really need to be careful how you present the results of the intelligent system to them. Because as we established, there will be mistakes in them. So better make sure that you don't overdo it with mistakes. Also don't overdo it with gathering feedback, because once you've asked the same user for the 10th times, if this was a good interaction for them, they will get annoyed quickly. So there's also a lot that can go wrong here. And of course, this is a very high-level abstract visualization of this. Inside each of these boxes, you will find more boxes, and then maybe even more boxes inside them, boxes all the way down. And for each of those, there will be tons of other decisions that you have to take. How these elements interact, which quality requirements they should support, and so on. One of these quality requirements in AI-based systems, as we heard, will be, hopefully, environmental sustainability. And this is the last and most important part that I want to talk about, and this is green AI from a software architecture perspective. So most of this will be based on a paper that we published this year at the International Conference on Software Engineering, in the Software Engineering in Society track, where we basically tried to conceptualize reusable tactics that can make ML-enabled systems more environmentally sustainable. So luckily I don't have to motivate this a lot, because Nate already did a great job here. So I don't have to convince anybody here, I guess, that machine learning consumes a lot of energy, so it's very computationally demanding. We already also heard about this interesting statistic that a typical natural language processing model emits like 5 times the greenhouse gas emissions of an average car over its lifetime. The crazy thing that I always find when I hear this statistic is that it's from 2019. So it's really way before ChatGPT and everything entered the picture, so you can imagine how it's right now. So Nate already also mentioned that there are different things that consume energy with AI-based systems. So we have the initial R&D, then we have training and retraining, and then we have the inference. And of course, the first two require more energy per unit, so to speak. But if you do inference at scale, this also really can be a problem. So in this paper, they also have a figure that illustrates this. So don't look too much at the percentages, because this 1.4 is not really valid anymore. It's much higher now. And also how much AI contributes to the ICT sector is unfortunately also much higher now. But I like really this visualization here, so that in the initial development, this will consume a lot of energy, but it's very infrequent. And then if you do retraining, consumes a bit less, but is more frequent, and then you get to the inference. And if you have the inference really at internet scale, some things that Google and so on do, then it really becomes problematic. Or also OpenAI with ChatGPT. The more people use it, the more problematic the inference will become. We already heard that this AI boom torpedoes the climate goals of the big tech companies. So Microsoft announced that they want to be carbon negative, not even carbon neutral, but carbon negative by 2030. And this, of course, has been blown out the window by now. Similar for Google, so they also announced something similar, and they increased even more in their carbon emissions. This is a problem. The question now is, can green AI come to the rescue here? So you may have heard about this distinction in red AI and green AI. So it goes back to a paper from Schwartz et al., where they stated that red AI is basically AI research that really focuses on accuracy as the most important thing to optimize. So you use massive computational power to really get the last percentage point of accuracy with a complete disregard for efficiency and the costs. On the other hand, green AI still aims for good results with respect to accuracy, but they will also focus very much on computational costs and try to reduce the resources that are spent for this accuracy. So here the idea is that you promote approaches that are favorable with respect to this trade-off between accuracy and energy consumption. So you might lose a bit of accuracy, maybe
according to Wikipedia, energy.
Not even that much. But you will reduce your energy consumption by a lot. This is the idea here. And the good news is that green AI research is really progressing. So a recent review by Vrije et al., they found like close to 100 studies. So by now the number has even more increased. So people are really studying this, how we can reduce the energy consumption here. However, the bad news is that it's still fairly difficult to apply these scattered results, because they are, of course, in different research papers. Sometimes they might not even be really for practitioners, so it's difficult to apply them. Yes, please.
Now, you're talking about energy consumption, but how does that directly relate to actual emissions? Do you know that?
Well, I mean, if the energy that you use is not from green sources, then of course it will cause emissions, right?
Yeah, so there is, so in green AI,
yes.
Is there the green AI is not necessarily green, because if you lose less energy, that's great, of course, but if it's all gray energy, then it's not very green, is it?
That is true, definitely. But I think a lot of companies these days like to focus on carbon emissions, because then they don't have to reduce their energy that they use. So they kind of move their workloads to a different data center and use up the renewable energy that they have there without trying to optimize their own workloads.
Okay, so it's a bit of both, is what you're saying.
Of course, I mean, if we would have enough renewable energy, this would work, but we definitely don't. No. So it's imperative that we reduce the energy that we use. Okay, so we cannot solely solve it by reducing carbon emissions.
So would you say that the more effective approach right now is to reduce consumption opposed to using green energy? Yeah.
Yeah.
Okay.
Yes. This is the reverse card, and I had this question already, but especially because it's a combination between more correct and more energy efficient. Isn't this like the situation where Jevons paradox is like against you?
Yes, I agree. This is always something that I worry about with this research, that rebound effects might eat up the energy that we save. So that simply they train another model or use it more often. I'm not sure how we really can address this with constructive tactics to
because I was expecting a third factor then that's now missing to prevent it or something. But
yeah. I'm not sure if this is the regulators' task to do, to try to prevent this, but I agree. It's definitely a problem that energy that we might save with applying some of these techniques might get eaten up again in rebound effects.
Yes. Okay. Cool.
Yes. So how do we want to make this more actionable? So this is the question here. So currently we have research, we have some techniques, but it's difficult to apply them for practitioners. And we decided to approach this via the concept of architectural tactics. So these are fairly high level but reusable design decisions that focus on achieving a single quality attribute in a software system. So now you might ask, okay, that sounds familiar, isn't that like a design pattern? And the difference here is that patterns focus much more on a concrete problem. So they may also cover multiple design decisions, and they are often concerned much more with trade-offs. Tactics, on the other hand, are fairly high level. They focus on improving a single quality attribute, and they can be the building blocks that you have for patterns. So our goal here was basically that we want to provide actionable design guidance to improve the environmental sustainability of machine learning enabled systems. How did we do this? I won't bore you too much with the details, but there were two parts. The first was a literature-based synthesis where we looked at this research and then conceptualized reusable techniques from it, so tactics basically. Then we took this initial catalog to a focus group where we had 3 experts on software architecture for machine learning enabled systems. We refined it, added additional tactics to the catalog based on their feedback, and the final goal, the final contribution was then a catalog of these 30 tactics that we have here. So I will talk about some tactics, but before I get into this, I want to briefly tell you the best green AI tactic of them all. And Nate already mentioned this. Only use AI for solving a problem when it actually makes sense. So yeah, before it was said for Gen AI, I will repeat it for all AI. So there is a right problem for AI, or the right problems, and Geoff Halton also talks about this in his book. So typically AI is very good for very large problem spaces. So if you have a massive scale of options, or even open-ended problems like books, movies, and so on, where yeah, every month you get a lot of new entries, so open-ended sets. It's also very good for time-changing problems, stuff like stock price prediction, ad placement, where previous solutions may be invalidated over time. And then there are just some problems that are intrinsically hard, so that are just so complex that it's basically impossible to solve them without AI. And this is, for example, human speech or text, then image recognition at scale, and there are also some games like chess or Go that are so complex that it would be very difficult to solve them without this. It's also very important that in the usage scenario, imperfections and mistakes are acceptable, because if they are not, you cannot use AI, because it will make mistakes. It's unavoidable. So always keep in mind, when you use AI, it must outperform the alternatives that you have. So it needs to be cost effective. So this could either be heuristics or also humans. So don't also forget to include the cost of mistakes. Sometimes these might not be a lot, might be a little hit that your brand image takes. Sometimes it can be more. The more autonomous and cyber-physical the system is, of course, the more the cost of the mistakes. Yes, please.
How are the cost of mistakes adding up to being green or not?
That has nothing to do with green here. So here it's just about deciding when to use AI.
Ah, sure.
Yeah. So here it's not about environmental sustainability. But of course this can also play into the equation. Yes. So this is the catalog. We used 6 different categories along the life cycle of the of machine learning enabled systems. So it starts out more with the data-centric tactics, then goes over algorithm design and the model optimization and training, and then more to the stages of deployment and management when the systems are actually out there in production. And I will go into a few of these as examples. And I will start with a data-centric tactic. So one tactic that is fairly effective, and we have a bunch of study by now on this, is apply sampling techniques. So naturally, the more data you use to train a machine learning model, the more energy it will consume, because it will become larger, it will also use more in the inference then, and it isn't always guaranteed that accuracy will substantially increase, especially if you add low quality data. So having a smart sampling technique like stratified sampling can really be an effective way to reduce the energy consumption while sacrificing fairly little accuracy. So this is a tactic that can be very effective if you curate a high quality but smaller data set. Similarly, there is another tactic in this space that is called reduce the number of data features. So the attributes that you use during the inference that you train your model on, if you have a lot of those, of course energy consumption will also rise again. So it is very important that you only add features that add substantially to accuracy. So sometimes you will have features that might add a trivial amount to accuracy or even none at all. These are also sometimes called epsilon features, and it's very important to identify them and then to remove them. Because the lower your number of features, the easier it also will be to maintain your system. Because each feature is of course also kind of a dependency. Another decision to take is which algorithm, so which type of machine learning model you will train, if you train yourself. And there are, of course, algorithms that are more energy efficient than others. So especially deep learning is extremely energy hungry because you also need to use a lot of data. But especially in the more traditional machine learning algorithms field, there are some that are very efficient. So KNN is one of those decision trees, linear models, but also naive Bayes. And if you compare those to something like SVM or also deep learning, they are just extremely efficient. That doesn't always mean that they will produce a less accurate result. So sometimes they are on par or even better in terms of accuracy. So best first try out with an efficient model, and if that doesn't really work, go to something more heavyweight. This was already mentioned, so of course even better than training yourself is using an existing model, a pre-trained one. So consider using transfer learning if a pre-trained model exists for your domain or use case, then try to use this, maybe fine-tune it, and you will save a lot of energy in training. So yeah, this is a fairly straightforward tactic, I guess. And the last tactic I briefly want to talk about is for the deployment and management stage. So this is about monitoring. Because if you have a machine learning system in production, what typically will happen that over time the prediction accuracy will drop. So this is something that is sometimes called concept drift, sometimes called data drift. But what happens is that the real world conditions can change and invalidate the statistical relationships that the model was trained on. So that means that after some time in use, it's basically inevitable that the prediction accuracy will reach levels where it's not acceptable anymore, and then you have to retrain. Some companies therefore do periodic retraining. So they retrain, for example, every week with new data and then deploy the new version. This, of course, can be effective, but it can also be wasteful because it's not a given that after a week already concept drift has happened. So what this tactic is trying to achieve is that you establish monitoring for when it's the best time to retrain your model. There are also some algorithms that you can use for this. Yeah, then you only retrain basically when it's necessary. So in these tactics, the 30 tactics, the majority of them focuses unsurprisingly on energy efficiency, but some others also on other quality attributes. Surprisingly, some of them even focus on accuracy. So even though we typically think about accuracy and energy consumption as a trade-off, we have some tactics in there that are intended to improve the accuracy of the system, but that simultaneously also reduce the energy consumption. And this is pretty great because it shows that green AI doesn't always have to be a trade-off. So all of this catalog is available online, but also in a web application that our research group has used for several years. So it's a bit dated by now, and we want to modernize it. But yeah, for the moment it will still do. So you will find all of these tactics also in there. One thing that is still difficult is that tactic selection often requires expertise. So either domain-specific ones or machine learning expertise. And this is made more difficult by the fact that not all tactics are universally applicable. So some are therefore worded with consider and some with use. Yeah, it's also important that some definitely will reduce the accuracy. And we need a bit more research on how this plays out, or also how we can reduce the impact on accuracy. so that it will be more easy for companies to adopt them. And lastly, we saw that most of the tactics are still focused on the training, so the models and also the data. But for the later stages of the life cycle, we don't have so much yet. So we also need more research there. So what we want to do with this catalog, we want to extend and refine it. We want to make the tactics more actionable so that it's easier for practitioners to apply them. So we want better descriptions, but maybe also code examples that can be copied and adapted. We want better tool support for this that makes it easy and convenient to browse the tactics. And we want to make it easier to select tactics, for example, by specifying requirements or your context, and then you get suggestions for tactics to use. Sometimes we will need additional evidence for their impact on quality attributes, especially for trade-offs. And we want to study how we can minimize these potential trade-offs. And lastly, it will be important that we do industry case studies about real-world scenarios, because most of the evidence that we have comes from controlled environments. But if, as soon as you go into a real-world industry environment, there are of course other forces that come into the picture, and we definitely need to check how we can ideally apply these tactics in real-world industry scenarios. So as my final takeaways, I talked to you about software engineering for AI as a way to create high-quality AI-based systems. I highlighted that architecture and design is very important here, but that knowledge about this is still in its infancy and is still forming. I also talked to you about green AI, why it's important, and that it doesn't always mean sacrificing accuracy, and that energy efficiency is something that ideally should be a system-level quality concern that that we try to improve over the whole life cycle of AI-based systems. So I'm very open for collaborations in this space, especially if you would be open to do an industry case study where we improve AI-based systems with some of these tactics to reduce the energy footprint. So feel free to reach out to me if this is interesting. Thank you.